The area rule. The Whitcomb area rule, also called the Transonic area rule, is a design technique used to reduce an aircraft's drag at transonic and supersonic speeds, particularly between Mach 0.75 and 1.2. This is one of the most important operating speed ranges for commercial and military fixed-wing aircraft today, with transonic acceleration being considered an important performance metric for combat aircraft and necessarily dependent upon transonic drag. A quick description on the subject. At high subsonic flight speeds, the local speed of the airflow can reach the speed of sound where the flow accelerates around the aircraft body and wings. The speed at which this development occurs varies from aircraft to aircraft and is known as the critical Mach number. The resulting shock waves formed at these points of sonic flow can greatly reduce power, which is experienced by the aircraft as a sudden and very powerful drag, called wave drag. To reduce the number and power of these shock waves, an aerodynamic shape should change in cross-sectional area as smoothly as possible. The area rule says that two airplanes with the same longitudinal cross-sectional area distribution have the same wave drag, independent of how the area is distributed laterally, for example, in the fuselage or in the wing. Furthermore, to avoid the formation of strong shock waves, this total area distribution must be smooth. As a result, the aircraft have to be carefully arranged so at the location of the wing the fuselage is narrowed or wasted so that the total area does not change much. Similarly, but less pronounced, fuselage wasting is used at the location of a bubble canopy and perhaps the tail surfaces. The area rule also holds true at speeds exceeding the speed of sound, but in this case the body arrangement is in respect to the Mach line for the design speed. For example, consider that at Mach 1.3, the angle of the Mach cone formed off the body of the aircraft will be about micro equals arcsine times 1 divided m, which is equal to 50.3 degrees. The micro being the angle of the Mach cone, or simply the Mach angle. In this case, the perfect shape is biased rearward or aft facing. Therefore, aircraft designed for high-speed cruise usually have wings towards the rear. A classic example of such design is the Concorde. When applying the transonic area rule, the condition that the plane defining the cross-section meets the longitudinal axis at the Mach angle micro no longer prescribes a unique plane for micro other than the 90 degrees given by the m equals 1 part of the equation given earlier. The correct procedure is to average over all possible orientations of the intersecting plane. Now to discuss a relevant topic, the Sears-Hawk body, which is a superficially related concept, but it is the shape with the minimum wave drag for a given length and volume. However, the Sears-Hawk body shape is derived starting with the Prattle-Goldwert equation, which governs small disturbance supersonic flows. But this equation is not valid for transonic flows where the area rule applies. So although the Sears-Hawk body shape, being smooth, will have favorable wave drag properties according to the area rule, it is not theoretically optimum. A bit of history on the subject, starting with Germany. The area rule was discovered by Otto Frenzel when comparing a swept wing with a W wing with extreme high wave drag while working on a transonic wind tunnel at Junkers Works in Germany between 1943 and 1945. He wrote a description on 17 December 1943 with the title Arrangement of Displacement Bodies in High-Speed Flight. This was used in a patent filed in 1944. The result of this research were presented to a wide circle in March 1944 by Theodor Zobel at the German Academy of Aeronautics Research. In the lecture, Fundamentally New Ways to Increase Performance of High-Speed Aircraft. Subsequent German wartime aircraft design took account of the discovery evident in the slim mid-fuselage of aircraft such as the Messerschmitt P1112 and P1106, and the indisputably wasp-waisted Focke-Wulf 1000x1000x1000 Type A long-range bomber, but also apparent in delta wing designs like the Henschel HS P135. Several other researchers came close to developing a similar theory, notably Dietrich Kuschmann, who designed a tapered fighter that was dubbed the Kuschmann Coke bottle when it was discovered by U.S. forces in 1946. In this case, Kuschmann arrived at the solution by studying airflow, notably span-wise flow over a swept wing. The swept wing is already an indirect application of the area rule. In the United States, Wallace D. Hayes, a pioneer of supersonic flight, developed a transonic area rule in publications beginning in 1947 with his PhD thesis at the California Institute of Technology. Also, Richard T. Whitcomb, after whom the rule is named, independently discovered this rule in 1952 while working at the NACA or NACA, which is a precursor to today's NASA. While using the new 8-foot high speed tunnel, a wind tunnel with performance up to Mach 0.95 at NACA's Langley Research Center, he was surprised by the increase in drag due to shockwave formation. Whitcomb realized that for analytical purposes, an airplane could be reduced to a streamlined body of revolution, elongated as much as possible to mitigate abrupt discontinuities, and hence equally abrupt drag rise. The shock could be seen using the Schillerin photography, but the reason they were being created at speeds far below the speed of sound, sometimes as low as Mach 0.70, remained a mystery. Then in late 1951, a lab hosted a talk by Adolf Busemann, a famous German aerodynamicist who had moved to Langley after World War II. He talked about the difference in the behavior of airflow as speeds approached the critical Mach number, where the air no longer behaved as an incompressible fluid, whereas engineers were used to thinking of air flowing smoothly around the body of the aircraft at high speeds. It simply did not have the time to get out of the way, and instead started to flow as if it were rigid pipes of flow, a concept Busemann referred to as stream pipes as opposed to streamlines, and jokingly suggested that engineers had to consider themselves pipe fitters. Several days later, Whitcomb had a eureka moment. The reason for the high drag was that the pipes of air were interfering with each other in 3 dimensions. One does not simply consider the air flowing over a 2D cross-section of the aircraft as others could in the past. Now, they said, they also had to consider the air to the sides of the aircraft, which would also interact with these stream pipes. Whitcomb realized that the shaping had to apply to the aircraft as a whole rather than just to the fuselage. That meant that extra cross-sectional area of the wings and the tail had to be accounted for in the overall shaping, and that the fuselage should actually be narrowed where they meet to more closely match the ideal shape. Moving on to applications, the area rule was immediately applied to a number of development efforts. One of the most famous was Whitcomb's personal work on a redesign of the Convair F-102 Delta Dagger from the U.S. Air Force, which was a jet fighter that was demonstrating performance considerably worse than expected by indenting the fuselage beside the wings and, paradoxically, adding more volume to the rear of the plane. Transonic drag was considerably reduced, and the intended Mach 1.2 design speed was reached. The culminating design of this research was the Convair F-106 Delta Dart, an aircraft which for many years was the U.S. Air Force primary all-weather interceptor. Numerous designs of the era were likewise modified in this fashion, either by adding new fuel tanks or tail extensions to smooth out the profile. The Tupolev Tu-95 Bear, a Soviet-era bomber, has large bulged landing gear nacelles behind the 2 inner engines, increasing the aircraft's overall cross-section aft of the wing root. Its airliner version has been the fastest propeller-driven aircraft in the world since 1960. The Convair 990 used a similar solution, adding bumps called anti-shock bodies to the trailing edge of the upper wing. The 990 remains the fastest U.S. airliner in history, cruising at up to Mach 0.89. Designers at Armstrong Whitworth took the concept a step further in the proposed M-wing, in which the wing was first swept forward and then to the rear. This allowed the fuselage to be narrowed on either side of the root instead of just behind it, leading to a smoother fuselage that remained wider on average than one using a classic swept wing. One interesting outcome of the area rule is the shaping of the Boeing 747's upper deck. The aircraft was designed to carry standard intermodal containers in a too wide, too high stack on the main deck, which was considered a serious accident risk for the pilot if they were located in a cockpit at the front of the aircraft. They were instead moved to the above deck in a small hump, which was designed to be as small as possible given normal streamlining principles. It was later realized that the drag could be reduced much more by lengthening the hump, using it to reduce wave drag, offsetting the tail's surface contribution. The new design was introduced on the 747-300, improving its cruise speed and lowering drag, with the side effect of slightly increasing capacity on passenger flights. Aircraft designed according to Whitcomb's area rule, such as the Blackburn Buccaneer and the Northrop F-5, looked odd at the time they were first tested and were dubbed the Flying Coke bottles. But the area rule is effective and came to be an expected part of the appearance of any transonic aircraft. Later designs started with the area rule in mind and came to look much more pleasing. Although the rule still applies, the visible fuselage wasting can only be seen on a few aircraft such as the B-1B Lancer, the Learjet 60, and the Tupolev Tu-160 Blackjack. The same effect is now achieved by careful positioning of aircraft components, like the boosters and cargo bay on rockets, the jet engines in front of and not directly below the wings of the Airbus A380, the jet engines behind and not purely to the side of the fuselage of a Cessna Citation X, the shape and location of the canopy on the F-22 Raptor, and the image of the Airbus A380 above showing obvious area rule shaping at the wing root. This is seen on the screen, which is practically invisible from any other angle. This has been a presentation on the area rule. Here are some of the references. Thank you for listening and watching.